We'll start in English. Thanks for the invite to do this presentation. I mean, as it was asked, this is more like an informal talk. So I will talk today about explainable AI and its relation with robustness and generalizability. And so, as Elder said, I did my PhD here in machine learning, mostly in explainable AI, but also it was very much focused in an application related with breast cancer. I also studied here, so I did my bachelor and my master's in electrical and computer engineering here at the University of Porto, and then PhD at the University of Porto and here in the group. And for some time, I also went abroad, and I was a visiting student at the Karlsruhe Institute for Technology in Karlsruhe in Germany during my master. I did 1 year there. And then during the PhD, I was a visiting student at the University of Bern and the medical university there in Switzerland, where I was working closely with radiologists. And well, right now, I'm an assistant professor at Utrecht University, where I'm focused on explainable AI for life science data. And I'm also a postdoc and an AI researcher at the Netherlands Cancer Institute, where I lead a research line at the Department of Radiology, focused on trustworthy AI and AI for multi-center data. So I think right here you can see the connection between explainable AI and robustness and generalizability. And I'm also an external senior researcher, is that the correct name, at the group, meaning that I'm collaborating in a research project and supervising some master students. So basically, my life is in between those two cities, the two most beautiful Dutch cities, Amsterdam and Utrecht. Sorry, am I wrong? Yeah. They're the best cities in the Netherlands, so if you didn't visit yet, you should. And well, from time to time, I also come here to eat francesinha with some of these guys. And well, I think today we will do the same. So just giving an overview of the research I'm doing. So I think in general, you could say that the research falls into trustworthy AI. I work in these three topics. So the first one is explainability, as well, the name of this presentation already says. So like here, the goal is to understand predictions, of course. Basically, that's the initial goal of explainable AI. But besides that, you can also use explainable AI to try to identify relevant clinical information. So here there are two main tasks: understanding the predictions of the models, but also trying to do clinical discovery. So there are a lot of tasks that medical doctors already know how to solve, and then you use AI just to help things be faster. And then you just like want to understand what is behind the AI decisions. Is it in accordance to the clinical knowledge? If yes, then you can trust the decisions. But there are some scenarios where even medical doctors don't really know. For instance, for treatment selection and treatment prediction, well, clinicians still don't know exactly the patients will respond to a treatment and why. So also trying to use explainable AI to get more knowledge in that sense. And then the second topic is about generalizability. So in the medical field, you usually work with data sets acquired from different centers. And we want to make sure that AI models are robust against these domain shifts. And here, well, there are several approaches you can follow. So one is like entitled representation learning, where you try to separate the different sources of information. Another one is trying to like use some inductive bias. So like you have some expert knowledge that you can use and you can embed in the model so that it becomes more robust. And more recently, I'm also researching on like self-supervised techniques to help improve robustness. And the final topic is about privacy. It was something that I started during my last year of the PhD. So the goal here is to develop privacy-preserving machine learning, and then like explainability for these privacy-preserving models. So we can think about these in like two ways. The first one, that was what Elena was doing and still is doing, is more like we learn everything in a centralized way, but then we want to share explanations as case-based explanations, and then we need to visually anonymize the images. And another way is to learn in a decentralized way, so following like federated learning. And this means that the data never leaves the hospital, but just like you learn across the hospitals without needing data sharing. And this brings some challenges that I will talk briefly at the end of this presentation. And well, the right side, you can see like all the students I have working on these topics, and some are not students anymore, like Daniel, but is still working on these problems. So, like, I think all of you already heard about explainable AI, but I bet it was mostly about saliency maps, which is the most common way of generating explanations, at least for computer vision purposes. But this is what I call as like prediction understanding. I mean, you don't really, this helps for sure, this is useful, because it highlights the regions of the image that contributed the most to the decision, but I mean, there is no semantic meaning attached to these highlighted pixels, so it could be very difficult to understand the explanation. Because I mean, for instance, especially when you are dealing with binary classification problems, I mean, the same region could contribute to both decisions. So at the end, is it really explaining anything relevant? So this is one of the problems. So it just gives you a weak understanding of the models, not a very strong understanding. And besides this like weakness in the explanation, most of them are also not trustworthy. So I mean, you use explainable AI because you want to trust the models, but if the explanations that you generate are not trustworthy, then what's the point? And there are several articles showing that they are not very robust, and I just picked one that is very recent, so this was published last month, and it was like specific of radiology, but the conclusion is shared across multiple papers. Most of these saliency methods are vulnerable to subtle perturbations of the input, so you can have adversarial attacks that change completely the explanations. And I mean, I'm not just criticizing saliency maps, case-based explanations, which was something that I worked on myself, is also not very semantically rich. So you just explained by finding the most similar case from the past. It's super useful, especially in radiology, but still you don't deeply understand the decisions. You just have a sense of what the model did. So what I'm going to talk about is, again, like explainable and robust medical AI. So this, I see those two fields as two sides of the same coin. And well, what I did during my PhD was to use explainable AI to try to improve task performance. And in this case, it was related with medical image retrieval. So like what we know from radiology is that like the case-based explanations are extremely useful, not just to explain model decisions, but also as a computer-aided diagnosis. So it helps, the case-based explanations help the radiologists make diagnoses. So it's really important to find the most representative cases from the past, the most similar ones to the one we are currently diagnosing. And what we know from from the medical field is that usually the relevant information is spatially constrained. So it's just on like a very small region of the image. And most similarity metrics basically analyze the entire image. And what we know is that general image similarity is not the same as disease similarity. So we were trying to find a way to compute disease similarity instead of image similarity. And what we did was to use saliency maps to learn in a like weakly supervised way, because we only need the labels. We didn't need the locations of the disease, because if we have the labels, we could train a classifier to predict the disease, and based on this classifier, generate the saliency maps that give us the location of the disease features. And if we focus the representations on these disease features, then we can compute in a better way disease similarity. And this is what we did, and we were able to improve medical image retrieval by doing so. And more recently, what we did was to try to explore these saliency map methods to improve segmentation in multi-center data. And this was the work of one of my PhD students, Valentina. So we were working on multi-center colonoscopy data. And the goal, so the task we were trying to solve here was polyp segmentation. And as you can see in this image, I mean, the projector is not of the best quality. But what you can see in these images is that, I mean, there are some confounders to the image that are related to the center, but not related to the disease. So as you can see, like these, for instance, these boxes on the bottom left corner, sometimes there is like some text, some information here on this corner as well. And basically what we observe is that, well, like these domain shifts, as you know, like in general, domain shifts lead to drops in performance. And it was the same in this application. And well, you have like two different strategies that you can try to like improve the robustness of the models to these domain shifts. One is disentangled representation learning, and another thing that you could try is use new data augmentation strategies, and it was exactly what we proposed. So what we did was to come up with this innovative data augmentation strategy that uses the interpretability saliency maps to try to move the focus of the segmentation network to the anatomical regions. So the process basically starts with at first we have a center classifier pre-training. So we have, because we have like, in this case we have 6 centers. In training we are just using 5, so one is always kept outside the training framework for out-of-distribution assessment. But based on these like 5 centers, we train a classifier just to predict the center, because these like confounders are usually center specific. So if we are able to predict this, the center correctly, and if we generate these saliency maps will highlight the regions that are dependent of the center, and this is precisely the regions that we don't want to pay attention to. And after we generate these saliency maps, what we do is we use them as an augmentation strategy. So, and we do so for 2 types of approaches. So like for normal UNet training, but also for disentangled representation learning networks like the SDNet. So these disentangled representation learning networks, what they do already, or what they aim to do, is to separate the anatomical features from the style features. What we observe is that, okay, they do it to a certain extent, but they still consider some of these confounders that we want to get rid of, they still consider them as anatomical features. So we also want to make it more robust in this sense, and we also do this interpretability augmentation even in these more complex networks. So I mean the approach is very simple. We just like multiply in the case of the UNet, we multiply the original image by the saliency map with the probability p. So we don't do it all the time because otherwise the distribution of the test images would be completely different from the training. And in the case of these internal group representation learning networks, we don't do this multiplication in the original image, but instead we do it in the content channels. Because, I mean, these networks, they first try to separate content from style, and then if in the content information there are still confounders, then we try to avoid the network paying attention to that. And so basically what we observed is that like the segmentations had reduced noise levels, and it turned out to be better at detecting small polyps, which were like the most difficult ones. And overall, we observed an improved performance for out-of-distribution data. And I mean, in terms of out-of-distribution, we considered each of the centers at one time as out-of-distribution. So all centers were evaluated, and all centers showed an improvement with this interpretability strategy. And then, kind of in the same line of reasoning, but so in this segmentation model, we were using like interpretability as like learned by the saliency map methods for like classification, and this was the master thesis work of Daniel. What we did is like we have some domain knowledge about what should be the case. And then we tried to integrate this domain knowledge in the network so that it turned out to be more robust. Again, like the same things that happen for segmentation happen for classification. So like AI models are sensitive to confounders. And what Daniel observed was that well, like image acquisition and preprocessing vary across different data sets. And one of the things that varies is the windowing settings that the radiologists use to assess, to do the diagnosis. And I mean, like some of the data of the publicly available data sets have the original data, but others only have like the JPEG images that were acquired with these settings. And this means that there are like changes in terms of contrast and brightness of the images. You can see them here at the right side. And we basically were able to divide them in 3 different clusters. So, I mean, we have these, but what we know is that the diagnosis should be invariant of the data set or the windowing settings. So what we proposed were like 3 loss terms to try to make these classifiers more robust. So these losses, or like 2 of these losses, were only possible because in like one of the publicly available data sets we have both the original images in the DICOM format, and we are able to sample by using the windowing settings an image like representative of one of these clusters. And what we can do by having these pairs is that we can like promote similarity of the attention maps between both with regards to the disease, because I mean the disease doesn't change from the original image to one of the sample images. The disease should be the same. What changes is the windowing settings. So these windowing settings representations should change. So like we have like 2 losses related to this like similarity and dissimilarity. So like we try to promote a similarity between the attention maps of like applied to these both images in terms of disease, and we want that windowing attention maps are dissimilar because the windowing settings are different from one to the other. And besides that, we want that the latent representations are kind of blind to the opposite task. So we want the latent space related to disease to like be blind with relation to the windowing task. So basically, and the opposite, and that is made by using this equal probability loss. So if we have the representations of the disease, we should be unable to predict the windowing settings, and if we have this latent representation of the windowing settings, we should be unable to predict the disease. And basically what we observed is that this approach was able to outperform the baseline, and it did so across 3 auto-distribution datasets. The training was done with RACs, and then we tested the Vimy, Shakespeare, and Vietnamese chest X-ray dataset. And in all 3 of these auto-distribution datasets, our approach proved to be better than the baseline. And we do that without compromising in distribution performance, which is also very relevant. So, as I said initially, like robustness and explainability are 2 sides of the same coin, but if we introduce privacy, we don't even understand what is the coin. And so by using federated learning, I don't know if you're familiar with federated learning, but so in federated learning, you don't share the data, but you just share what you learn locally. And I mean, the point of using federated learning is because in the medical imaging domain, it's very difficult to share medical data, meaning that if you don't share medical data, your models will be learned with just a small data set. So they will not be as robust as they should because they didn't see enough variety in the data. So you want to increase the variety in the data, and since it's impossible to do that in a centralized approach because sharing data is problematic, you have to do that in a decentralized way. Meaning that if it's already difficult to explain deep learning model because it's super complex, when you have access to the data, when you don't have access to the data, it's even more difficult to understand the decisions. And well, if you want to have explanations for model decisions, you can try to anonymize them first, and I think all of you are familiar with Elena's work. But so basically, the idea, like when Elena did her master thesis, was that, well, we generate some case-based explanations, and then we want to share these case-based explanations, for instance, in a chat, or like in a medical chat, where we are just discussing cases, and then we want to show one of the past cases so that the radiologist is able to diagnose. But we can't, because there are privacy guarantees that you have to obey, especially with related to GDPR. And just like one important thing that I think like most people question about this is, oh, okay, but like if you have a chest X-ray or a CT, I mean, can you really recognize the patient? No, but like but for instance, if you have brain scans, then you can. And even if you can't recognize the patient, if you are able to do re-identification, so if you know that 2 radiology images are of the same patient, that's already a violation of GDPR because you have re-identification of patients. So if you want to share the medical data, in this case for case-based explanations, you have to anonymize it first. And this was what Elena did for her master thesis and is doing for her PhD thesis. So the goal here is that you're able to preserve the properties that are needed. So in this case, like realism and the explanatory evidence of case-based explanations. But at the same time, you don't expose identity. And she did that with like some privacy-preserving machine learning models that dependent on GANs and variational encoders. And this was the last work I collaborated with her. And basically the idea here was to separate identity and medical features so that you are able to just hide the identity and keep all the disease features that are relevant to explain the decisions. And this is also quite nice because with this type of approach where you disentangle identity and medical features, you can very easily generate counterfactuals. So you can generate the cases of the opposite disease. And what I did more recently was to try to do something similar, but in the context of federated learning. So as I said, we are in the medical field, we are moving to federated learning. Well, case-based explanations are very useful in radiology, so we still want case-based explanations, but well, we want these case-based explanations in a federated learning model. And basically what I did with Laura, who was a master student from VU in Amsterdam, what we did was first, we created this discriminative federated model, learning in a decentralized way. And then what we did was to have a generative model for each of the nodes that could generate synthetic data. And then based on these synthetic data bases, we could extract the case-based explanations. So these case-based explanations come from a synthetic database instead of the original database. And the synthetic data is composed of anonymized images. And that's it. So if you have any questions, feel free to ask.